Statistics is all around us. We use statistics to understand where to build hospitals and schools, how to develop new medications safely, to predict trends in the stock market, to forecast the weather, and so much more. Statistics can also help us bring clarity and understanding to complex situations. Take, for example, the COVID-19 pandemic, which turned the world upside down in 2020. Statistics played a vital role in keeping Canadians safe. Of course, we all know that statistical modeling directly affected policy decisions, such as the decision to close schools and limit social gatherings. What might be less obvious is that statistics and probability can also be key in limiting the spread of misunderstandings which have arisen throughout the pandemic.
Recently, social media feeds have been overwhelmed with vaccine misconceptions. For example, you might have heard criticisms of the vaccine that take the form,
"The vaccine doesn't work. If it worked, why would we need to continue to wear masks and socially distance?"
Let's say we wanted to run an experiment, such as a COVID-19 vaccine trial, on some target population, represented by these poker chips here. These chips represent every human that exists now and ever will exist. There's a lot of varying characteristics between members of our target population, which is represented by the different colors of the poker chips. For example, maybe the red chips represent children, the blue chips represent the elderly, and the white chips represent everyone in between. In reality, we'd have more than one characteristic and more than 3 different groups, but stay with me here for the sake of the analogy. Ideally, we want to run our experiment on our entire target population. This isn't feasible though. We don't have access to our entire target population and instead only have access to what's called the study population. In the case of the vaccine, our study population is composed of individuals living during the COVID-19 pandemic, which in turn means they likely follow strict social distancing guidelines and wear masks. From here, we'd like to include our entire study population in our experiment, but this is also unrealistic. Instead, we select a representative sample of our study population and perform the experiment using this subset, which we'll call the sample. Now, to get our results, we perform the vaccine trial on our sample. Assuming that the sample is representative, we can generalize our results from the sample back to the study population. Assuming that the study population is representative of the target population, we can generalize our results there as well. Earlier, we mentioned that our study population was composed solely of people living in the COVID-19 era, who are subject to social distancing and mask-wearing policies, and the target population consists of all humans now and into the future. As a result, the study population is not representative of the target population. The vaccine trial can only make conclusions about people living when these restrictions are in place, not when they have been relaxed. Note that this does not mean that the vaccine doesn't work without these policies. It only means that these studies cannot tell us this information. So whenever you hear,
"The vaccine doesn't work. If it worked, why would we need to continue to wear masks and socially distance?"
remember that the caveats surrounding the vaccine are there to ensure that our target population continues to match our study population. A study population where we know the vaccines are incredibly effective.
Another misconception that's been circulating the internet is about COVID-19 test accuracy. Recent statistical analyses suggest that the tests are somewhere between 95 and 99% accurate. However,
if you're testing in a population that doesn't have very much COVID, you'll get false positives almost half the time.
you might have heard people say things in response to this like,
"False positives 50% of the time. That sounds to me like the testing is very unreliable."
this demo illustrates why these two statements are not contradictory. Here we have a population of 2,500 individuals where only 25 of them, or 1%, have COVID. We will assume that the test returns correct results 99% of the time. If we test all members of the population, the expected results are shown here. We can see that all 25 of the positive COVID-19 cases were correctly identified, but 25 people who did not have COVID-19 came back with false positives. In total, there were only 25, or 1%, incorrect test results, so the test had 99% accuracy. However, 25 out of the 50 positive tests were actually false positives. This is where this quote comes in.
If you're testing in a population that doesn't have very much COVID, you'll get false positives almost half the time.
Because our population only had a 1% infection rate, Bayes' theorem tells us that we'll get false positives 50% of the time, even though we have 99% accurate tests. Statistics is essential to understanding the world around us, especially during the pandemic.